feeling like sunshine, like springtime, like something's in the water and I'm taking a deep dive. I'm feeling so weightless, like I'm gonna make it, and nothing in the universe can take this. I can see it clearly now, nothing gonna bring me down. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong in my happy place. I got my head held high, I'm on my way, and I'm following the signs to my happy place. I'm walking in the light of a brand new day, and I'm right where I belong in my happy place. And I'm right where I belong in my happy place. And I'm right where I belong in my happy place.
Welcome to the National University of Singapore Yong Loo Lin School of Medicine Healthy Longevity webinar. It's wonderful that you are joining today. Boris Djordjevic is with us tonight talking about partial reprogramming. I am sure that this will trigger many questions, so please use, as always, the Q&A function to enable the conversation. Also, as always, we are starting with a short presentation, and today by Dr. Weilan Wang, and she is postdoctoral fellow at the NUS Academy for Healthy Longevity. She presents on her own research about mortality risk prediction among geriatric rehabilitation in patients, and she is using a machine learning approach.
Thank you for the introduction. As mentioned, I'm Weilan Wang, and today I'm going to share my work on all-cause mortality risk prediction among geriatric rehabilitation population and its risk factors. And we are going to use an interpretable machine learning model to achieve this. Firstly, let me introduce you who is the geriatric rehabilitation in patients. They are patients being admitted into the geriatric rehabilitation ward after being discharged from the acute event. In the rehabilitation center, they received comprehensive geriatric assessment and also individualized rehabilitation to restore their function capacity. These patients, they usually have multiple diseases and most likely facing functional decline and in suboptimal health status. So in this study, we are trying to establish a machine learning model to predict the risk of mortality among these patients and after discharge. And we are also trying to investigate the importance of each factor in this machine learning model to predict mortality risk, and which is also more likely to know as the risk to death after the discharge. And this is the timeline of our study, as we mentioned before. And they were admitted after the acute events into the rehabilitation center. And after a time in this ward, they were discharged to home. And we follow them at 3 months, 1 year, and 2 years. The total number of participants is 1,874. And we track their mortality risk after discharge. We use a lot of characteristics and the features to predict the model, as you can see in this list. In this study, we use the XGBoost for the mortality risk prediction. And after building this mortality risk prediction model, we use the SHARP method to assess the risk importance of each feature. Here you can see that we use a lot of metrics to assess the performance of our model. Well, but generally speaking, this model achieved quite satisfactory outcome. As you can see in this column, that's the AUC, ROC are all over 0.75 in 3 months, 1 year, and 2 year mortality. So in summary, we are quite happy with the outcome of this model. The next step we are doing is to assess what are the important features in the prediction of death after the discharge. And we can see that the Charlson comorbidity score showed a very important feature. in 3 months and 1 year prediction, they are the most important. It is the most important feature. And in the 2-year mortality risk prediction, it is second most important feature. The higher this score is, the more severe or the more comorbidity the patient is having. Another important factor we can see here is the sarcopenia. Sarcopenia is the loss of muscle mass and the loss of fast muscle function. And it is also very important in the mortality risk prediction. And followed by the blood urea. This is a feature most people may not know, and this is highly associated with the dehydration in the population and also chronic kidney dysfunction. And another factor I want to highlight is the malnutrition screening score. The higher the score is, the higher the risk of the patients having malnutrition conditions. So this is also highly associated with the 3-month mortality risk. What we can learn from this study, and the first thing we can say that from this study, we establish a model using the XG boost, having satisfactory performance in post-discharge mortality risk prediction. And after the interpretation of this model, we can see that the comorbidity is the most important feature in 3 months and 1 year mortality risk prediction. It is also the second important feature in the 2-year mortality risk prediction. Other features, including dehydration, chronic kidney dysfunction, sarcopenia, malnutrition, and age, are also highly associated with the high mortality risk. Thank you for joining to my presentation. If you have any question about this study, please feel free to contact me via this email. Thank you.
Thank you, Welan, really showcasing that machine learning models now also reach geriatric care and even geriatric rehabilitation. It's my great honor now to present our guest. Boris Djordjevic is the founder and the CEO of 199 Biotechnologies, where he focuses on cellular reprogramming techniques to address chronic diseases and, of course, fundamental causes of aging, maybe the hallmarks of aging. He is also leading the Longevity Research Center in London, focusing on translating aging research into clinical applications through advanced bioengineering approaches. And just one of the examples is the 3D organ on chip models. His work really is bridging science and clinical practice solutions aiming to enhance human health and lifespan. So thank you so much, Boris, to be here. Love to give you the floor.
Okay. First, thank you very much to Andreas for this opportunity. Also, very good talk from Dr. Wang. And I will now start to talk a little bit about this partial reprogramming, which is something I spent the last few years and I figured this is something that is emerging as a really transformative strategy, both in aging research, in regenerative medicine, and it is something which is very interesting, where this expression of these pluripotency factors can reverse many of the hallmarks of aging. And out of the 12 of the hallmarks of aging, more than half are connected to these epigenetics, to these gene expression, to these nutrient sense. I mean, all of them are in a way interconnected. And there is a lot of very interesting things going on in this aging research, and it is really exciting to be able to transform and bring something out of this aging research to hopefully to patients very soon. So epigenetic reprogramming or partial reprogramming is really this modification of the DNA that regulates the gene expression without really changing the underlying sequence. And this modification, they can turn genes on and off and influence how much of that gene is expressed in the cell. And this research in partial reprogramming has started first with this iPSC, the research in stem cell. And this research in stem cell, especially these Yamanaka factors, are something that I like to call as a cheat code in biology. I don't think there is anything else in biology that can achieve such a substantial effect in cells, that can transform completely what a cell does. And just these six Yamanaka factors have shown these amazing results in terms of changing completely like a cell function, even from an old cell into this pluripotent state. And maybe that the little child of this research in the last few years has been this partial reprogramming, where the scientists have dialed down a little bit this iPSC like transformation into this partial reprogramming. And by expressing only some of these reprogramming factors for a much shorter time than what is necessary to achieve this iPSC state, the research has shown that we are able to essentially turn back the clock in a cell to restore a much younger like phenotype in terms of how the cell function, which genes are on and off. And that's something which is extremely interesting, because normally it does happen only one time in our life. So this machinery to reset the age of the cell is something that is only turned on at a single point in time during embryonic development, and otherwise we would be born old. And the only reason we are not born old is that epigenetic reprogramming is something that happens naturally in our body. And now in the sciences, we are looking how can we use that mechanism not during just this embryonic development process, but to use it at any point in time, even at old age, to reset better and younger function for the cells. So as we age, there is this epigenetic erosion. So what I like to call this epigenetic erosion is when the cells do not function as well. And this is, just a second. So as aging is one of the big risk factors that leads to many diseases, such as type 2 diabetes, neurodegenerative disease, cardiovascular disease, we don't really understand very well all the mechanisms of aging. However, now it's really emerging that this progressive decline of these maintenance systems, this epigenetic regulation, gene expression, is like this sort of multifactorial nature of this biological aging is really bringing out and accelerating that, all these diseases. So these like one would be this aging and cancer, and this genomic instability, aging and cancer is very much very much core to that disorder. The second, whether it's autoimmune disease, in a way, being able to reverse, even not with high fidelity, this gene expression, this protein production and so on, would have impact in aging, cancer, potentially in autoimmune disorders, in neurodegenerative disease, in things like the ovarian aging, sterility, in muscle-related disorders, genetic disorders, and potentially even some broader things like cellular senescence, and maybe to precise a little bit what I mean by this epigenetic erosion, I really mean this gradual loss and disruption of the normal cell expression, these normal patterns over time, especially as organisms age. And this epigenetic erosion globally on a cellular level, it looks like this increased variability in gene expression, the loss of cellular identity. So the cell, they tend to forget a little bit what they're supposed to do. For example, a skin cell might end up doing something that a brain cell or heart cell or another type of cell would be doing. And when we're young, all the cells in one tissue, they work very much well together. But then you start to have this loss of homeostasis. And this is translating into what we know as aging. And it is linked, for example, with this mitochondrial dysfunction. So this increased oxidative damage, this depletion in NAD, these changes these metabolic changes, and this epigenetic erosion is something that we really believe is core to that aging, and we would like to address. So maybe I will just skip a little bit forward. It is also core, for example, we looked at potential in muscular dystrophies like FSHD. Although it is a genetic disease, our body has this ability to control and regulate this DUX4 production, which is what is linked at for the facioscapulohumeral muscular disease. And if we can restore the ability of the body to regulate this gene production, then it might be an avenue to target even diseases such as FSHD. And this research in partial reprogramming, epigenetic reprogramming, has already shown a lot of in vivo data. For example, recently in hypertensive mice, where this partial reprogramming, where restoring the normal gene expression and the function of the cells can basically reduce blood pressure and also many other factors for the disease model mice. The same in vision. One of the more famous paper by David Sinclair is the ability of using these reprogramming factors and doing that partial reprogramming to restore. So restoring a young DNA methylation and gene expression to promote again the regeneration of the axons, the damaged nerve fibers, and restore vision in mice. There is more data in the glaucoma, so where both in mice, and there was recently also in non-human primate where this partial reprogramming has restored vision. And again, we saw the same in the heart or liver tissues. We saw the same in maybe more broadly. This partial reprogramming has shown to be able to extend lifespan, maybe modestly by 10%. Although there is a more recent data from Altos Labs which has shown, I believe, up to 25% in the presentation. Although I haven't seen the data myself, and so partial reprogramming holds a lot of potential, and not just in rejuvenating cells, but doing so while preserving their unique role in restoring the normal cellular function resilience. As we age, we are becoming more and more susceptible to disease, and this has the potential to reverse that, to help with regenerating tissues, whether it's muscle, brain, or skin, and broadly extending the health span and the lifespan. So some of the first work that we did was in this microvasculature model. We wanted to see in these organoids, 3D organ-on-a-chip models, what does really happen when you do that expression of these reprogramming factors. And very luckily, in our company and also from the University College London, we have these organ on a chip that replicate this human microvasculature, and we're able to look at most of the parameters that you can see. For example, just a second. For example, look at all the dynamics. I look at the perfusibility, looking at this integrity of the vasculature, at whether there is leakage, and all these mechanical cues are replicated in that model. So here we go, and then we did. One of the first and most interesting work that we do is we use these patient cells, and we use to replicate this vasculature, you need at least two types of cell, the HUVECs and the fibroblasts, and we use the patient fibroblasts from young patients, and the patient fibroblasts are able to show this fully perfusible like vasculature. So the red that you can see is essentially a substitute for blood, and the young patient cells are able to hold these substitute for blood. While if you use the old patient cells, well, you have that leakage which is similar to what we can see in the brain. Is you have this leakage. The blood-brain barrier, for example, is not doing its function as well as it should. And the interesting part is when we take these old patient cells and we apply partial reprogramming, both using viral vectors and using these mRNA and liposomes, we're able to restore, at first, using the first method, slightly this pervasibility, but then by using these liposomes, we're able to completely transform these old patient cells into, not just the young phenotype, but in being able to regenerate young, fully functional blood vessels. And it is not just about the in a way how it looks, but is in terms of function, whether it's mitochondrial function, whether it's these lysosomes, the profile is getting much, much closer to that of a young cell. And this is something we looked at with P8 fibroblasts with very similar and very good results. And the next step that we wanted to see is whether this holds true using in the blood-brain barrier. And the blood-brain barrier is probably the model, which is something that protects not only just the brain, but is something that is in a way at the root of most neurodegenerative disease, as a blood-brain barrier is being damaged, as it's losing its ability to control what goes in, what goes in the brain. Then we start to see that inflammation, and which gets progressively worse and is leading Alzheimer, but also other diseases such as Parkinson, ALS, and so on. And so we started to look at what's happening. Are we able to reprogram things like the astrocytes? And are we able to, and obviously this is the part where things get very complex, but we're able. Again, we have begun to see very interesting data on that side. So partial reprogramming has a potential to help with neurodegenerative disease. At the same time, one question we had is, what about cancer? We know that cancer is primarily due to DNA damage, but then we still don't understand things very well. However, what happens in cancer is that cancer is still, cancer is still a cell which is fundamentally not functioning the way that it should. And if partial reprogramming is able to even temporarily make a cell function normally, then maybe it's something that can work in cancer. So we started to look at breast cancer cells, and we have seen that applying this partial reprogramming, 3 factors using this OSK, so OCT4, SOX2, and KLF4, has really stopped this cancer proliferation. The cancer cells stopped replicating. So we had to check in other types. So we looked at 2 types of breast cancer. We also looked at the glioblastoma in lung cancer, in colorectal cancer, and maybe some we haven't put there, but we looked also in things like liver cancer and pancreatic cancer, and it's exactly the same. This epigenetic reprogramming is stopping the growth of cancer, is also stop the cancer invasion. And which is extremely interesting, as it's something that might seem a bit paradoxical. In the early research in iPSC, we always associated cancer with this overexpression of some of these reprogramming factors, and turns out when you actually when you express them in cancer cell, you are doing the opposite. So we put a lot of focus on the brain cancer, on the glioblastoma, since it is one of the most difficult to treat at the moment. It's also orphan disease, and we have shown that partial reprogramming can inhibit this cancer proliferation, this invasiveness, and this migration. And maybe more interesting is when we look at what's happening, we start to see that cancers are not only they stop being cancerous, however, they start to look senescent, and after a while, they start to die. And it's very interesting. It's as if the cancer cells have realized that they have done something terrible and applied this, I mean, did, just like in Japan, this harakiri and suicide when they realized that how, I mean, what they have done. So this is a little video of this cancer migration. And you can see this was on, I believe, over 48 hours. And on the left, you can see the control where the cancer just keeps moving. And in a way is being evasive metastasis. And on the right, you can see that the cell, there are these blurs appearing, also these little darker parts at the cancer becoming senescent, and many of it dies. And again, in the middle, you see that empty channel still there, which means the cancer cells have also stopped moving from one place to another, which is what makes cancer really, really dangerous. Again, we looked at these tumor growth in spheroid models. So when you grow this cancer in these small little bundles, and are you able to stop this cancer? Are you able to reduce cancer? And we have seen this very, very big reduction in number of cancer cells for each of these spheroids. So it is something that's not just working in vitro, but works already better in these 3D models and shows some potential. Then we looked at the safety. What does it do in normal cells? And this is maybe what has been a bit unique in terms of what we do is, could we make this reprogramming more specific just to cancer? And in a way, to bring this aging research to patient is we have to make sure, we have to go through disease first, and we look how can we make this more specific to disease, more specific to cancer, and make sure it does not affect normal cell function. And again, we have seen that we have shown these first safety data on normal cells. We looked a little bit at the mechanisms of action and at things like this increase in P16, P21, and these various, ways through which the cancer, to really look whether it is really doing what it is doing. We have some early animal data in terms of where it goes and how it goes. And we are getting ready to do this phase 1 clinical trial for the glioblastoma at the moment. And maybe just before, I think my slides were a little bit shorter than I thought. So this partial reprogramming has, personally, we put a lot of effort in cancer, in brain disease, and more recently also in eye disease. But it's something that holds a lot of potential in not just, what we're working on, but pretty much most of the age-associated disease. So it's something we're very, very passionate into bringing to a patient. This is from many companies is not as easy. There are companies that focus more on understanding the science and understanding how it works. And then when they have these questions answered, it goes further and further and further. Being in biotechnology, being in the industry, and maybe it's a little takeaway message is being in the industry, we have this ability to take what is in the science and try to bring it to the patient. And maybe that's something which is, maybe that's a message that I want to encourage for any other people who are in the position where they can take these insights from aging research, from this longevity, and able to help patients or help bring it closer to the patient. And that's something that's ultimately maybe ethically really an imperative. So this is the end of the speech of this presentation. Here we go.
Good. Thank you so much, Boris. And I see that you're also searching for funding, which was on the last slide.
Well, I shouldn't have left that, but yes, obviously, like most companies, whether it's in academia or whether it's industry, we rely on funding. Doing this work is something which is it is labor intensive, it is cost intensive, and it doesn't make money until the stage you can become commercial. And aging research is maybe something which is a bit more difficult than even normal, like biopharma, just because most governments still don't think of aging as such a big problem. But it's changing, and I think Professor Andrea Maier is helping a lot on that side.
Oh, thank you so much. So kind,
Yes.
but I tried my best because I want this condition to be fixed. Um, but
Yes.
may I ask you first, maybe a personal question? Where is this 199 biotechnology coming from? Why not 201? What is 199?
Okay, so that's I think many people keep asking me that, and I'm not sure what to tell them. I can first have a bit of background from I mean in Asia, in China, and the number 9 is a very royal and good number linked to longevity, etc. So like 199 is a very nice number, both from this Asian and Chinese culture. On the other side, many companies tend to like these aging, this longevity in the longevity industry. They tend to put this goal. They want to extend the health span or lifespan by 5 years or 10 years, something like that. I said, well, that's not very bold. I mean, we are doing there. This is a technology that potentially can change, can extend that maximum lifespan barrier. So I think 199 is a good place, at least 199 years old, and is a nice number. Is also the house number of our labs in London. So
Okay, that's easy. So
yes,
hopefully there was not much marketing actually involved, and it was just you saw the number and then biotechnologies, it's done. But
yes.
it's great. Thank you so much for sharing. But what
Mhm.
you do in your business is really focusing on chronic diseases and even quite of rarer chronic diseases like glioblastoma. So we very often in our field say, yes, because it's aging, we have to start with chronic diseases. Is this really the case? So shouldn't we in the field a little bit more bold and say, okay, no, we as companies, as community, we are tackling aging first, and then we are tackling chronic diseases?
Well, so there is two versions, and when I talk to investors, obviously we have to target a disease. From ourselves, and why I started this company is, of course, I want to tackle aging, and it just so happened that the therapeutic for this chronic disease is exactly the same that you would use for aging if you were to deliver it systemically to the whole body. So I said, well, that's a very lucky coincidence, and in a way, we hope that once aging can really officially become an indication, then we would be in the best position to, to deliver the therapeutic, since we would already have translated it for disease.
Yeah, but on the other hand, don't we already have a couple of ICD codes, International Classification of Diseases, where we could say, okay, we could use them, like intrinsic capacity, vitality capacity. So isn't it that maybe the field should push towards operationalizing it, making sure that we can actually measure intrinsic capacity? I think we tried, or many groups tried to operationalize resilience, which is then intrinsic capacity, or very often being thought that then we can do the randomized control trials. You are doing it as a company. We are doing it in academia to be able to actually show you don't need that major event, having cancer, that we can stop actually the processes.
Oh yes, and ideally, the earlier you start, the better. In a way, preventive medicine is like you want to start to fix a problem before it comes, and it's probably the more cost-effective and fundamentally better approach for that. I do wish to see more of that. I'm not sure how soon and how well it's going to come, and I think perhaps you can answer that better than I could.
Yeah, no. And I absolutely understand from an investor's perspective that you first need a good indication. But that brings me actually to the next question, which is about your epigenetic erosion, you call it. We heard in the past months lots of noise that the aging process might not be linear. What about your epigenetic erosion? There was one paper talking about proteomics, that we actually age much faster. There are change points at the age of 40 and 60, might not be linear. What about your epigenetic changes? And that leads, of course, to when should we reprogram our epigenome and use your therapeutics in the end?
Yes, so I think there is still a bit of maybe a lack of of this understanding of exactly why it happens and how it happens. Is it what goes first? What is upstream? Is it this maybe perhaps this DNA damage, or there is another camp looking at this replication and just you have this loss of fidelity? But I think that regardless, I mean, and that's fundamentally that's the difference between academia and industry. In academia, you want to understand deeper and deeper and better. Perhaps I'm luckily on the camp where I don't need to understand more. I just have something which is very cool. I call it a cheat code in biology, and I just want to apply it the best way I can, in the safest way that I can, to the most people that I can. And in a way, I don't have to try to understand too much the nitty-gritty details, because there is a point at which we may know just enough, or at least with a certain degree of certitude what goes on, well enough at least to apply it and to help the patients and people and patients, whether they have a disease or whether they just have this aging, which is just as bad.
Yeah, but then I think, isn't it important to understand where really are changes occurring in the epigenome? So different methylations being expressed, sites being expressed. So shouldn't we know if aging is actually linear, or we have to really, once therapeutics are there, apply these therapeutics at certain ages? Is it at the age of 20 or 40 or 60, or just then when it already occurred?
For sure. Like I couldn't answer that question. I couldn't answer the question because this is probably quite far beyond my desk. But I mean, it is such an interesting point, and it also validates like we need both. We both need people who want to do this translation. We both need this fundamental research, and I think you cannot do one without the other. And for sure.
Yeah. Then. Let's ask me. I'll ask you. You told, okay, we try to achieve normal gene expression with the therapeutics. May I challenge you a little bit? What is normal? What is normal gene expression, knowing that there's a huge heterogeneity between your genome and my genome? Maybe not as huge as a mouse and you and me, but there is huge differences in alleles.
Okay, so I don't think there is exactly a very normal, at least across, that is common to individuals. That is very different for every individual. But for a single individual, obviously your gene expression is going to change over time for a variety of reasons. Some of them bad, some of them also good. I like to think as epigenetics as a sort of adaptation mechanism from our body to just change like the gene expression in a way that is more helpful for our survival. Perhaps we need more of this X protein, or we need maybe more melanin in our skin because we have a lot of the damage from the sun. And obviously our skin cell will begin this increased production for a good reason, and they will keep on doing that. So perhaps it's something desirable, but there might be cases where it's not desirable. For example, in type 2 diabetes, I like to call type 2 diabetes not a disease. I like to call it just a sort of adaptation of her body. It's adapting to this extremely dangerous and toxic nutrition, and is going to change like this insulin sensitivity and how our body handles all these sugars just because we have too much of it, and it's trying to protect us. And obviously that protection has its drawback, which is these I mean, all the dangers that come from these type 2 diabetes. So if we are able to restore, say you had a type 2 diabetes patient, and you apply that partial reprogramming on every single one of their cells, and you can restore that more normal gene expression, like I said, normal, at least more original, these original settings, then very likely the type 2 diabetes might be gone. However, if that person still continued his dangerous pattern of like eating patterns, then maybe that's also not so good. So it's a very hard question to answer. What is normal? What is not normal? But it's a cheat code, and for sure I want to abuse that cheat code. Like sometimes we don't need to play fair if we can find a way to achieve something good for the patients. And many of us are aging. Many of us have family members who are either
all are
over.
aging, isn't it?
I wouldn't want these people to be deprived of a therapeutic just because I do want to understand things a little bit more instead of trying to bring it a bit faster. So
yeah. So I think my question was a little bit to understand in the end, if you would apply precision neuromedicine, the approach, would you actually reprogram differently based on a personal genomic fingerprint in the end?
yeah, I think we have different kinds of cells, and whether it is terminally differentiated cells or cells that keep on replicate, and I think how the age is different. So it makes, I mean, I don't think there is a one single combination that can do the perfect job. I think the final version is going to be a bit tissue specific, and I don't think it's going to be as easy as like this single therapy, but probably a single therapy can still do some small amount of good. So we'll see how it goes. I do hope to have actually no, it's not. I'm not hoping. Is we are waiting for more animal data where we will actually know exactly how it's going to look like.
Yeah, I think you're one of the companies doing very specific 2D, 3D culturing methodologies, which is, I think, great, because you can use even human cells to impute them into your model. What do you think, how translatable is that from the 3D model into the in vivo situation, what we actually experience at this moment in time in all our bodies? So, because you invented it, you're using it all the time. Tell our audience a little bit where it's useful and where it might not be so useful.
Well, it's very hard to say as a scientist. There would be a huge amount of proof I would need to say with a good degree of certitude whether it's going to work or not, or whether it can be translated. I think the mechanisms through which it works is something that's as universally applicable, like whether it's in vivo or these 3D models, or even or in vitro or in vivo or 3D models. So we have a good I would say, I don't want to say gut feeling, but we have a good amount of certitude that it's going to work, and we have a lot of ongoing animal work to actually demonstrate that, and not just in cancer. But maybe there is one little interesting point, is that I'm sure you have heard about the naked mole rat, and for those who do not know, it's the naked mole rat is an animal that basically doesn't get cancer ever, and we're not even sure how long it can live.
Yes, we don't see you talking about the naked mole rat.
Well,
we don't.
It lives in the. I think I accidentally pressed the button. Here we go.
Yeah, now you're back.
Yes. So the naked mole rat lives in the dark, and there it is. And anyway, it doesn't get cancer, and we're not even sure exactly how long it can live. It doesn't seem, the risk of dying does not increase as the nickel rat ages. It also, the female nickel rat has this exceptional fertility at any age, doesn't lose any fertility. So in terms of ovarian aging is also amazing. And the interesting thing is there is very little data, but there is something that we notice, that some of these reprogramming factors are naturally expressed throughout the life of that nickel rat. So I like to say this might be one example where this partial reprogramming is actually seen in nature, and perhaps is the reason why that nickel rat doesn't get cancer, keeps that fertility, and doesn't seem really to age, in the sense the risk of mortality does not increase as it ages.
Yeah.
So there is at least some early basis in nature for what we're trying to do.
Yeah, I see already many questions coming in, but I have one final question. You're a founder, you're a CEO, you're a businessman, you love science. What keeps you awake at night?
It's I think it's creating an impact. It's being able to I came originally from a clinical background, so I studied medicine. And from medicine, I didn't choose to go the career of a doctor. I didn't choose to take the career of a scientist, because some people told me it's horrible. Once really you don't have time to do the cool science. You have to apply for grants all the time. I said, well, if I want to apply for grants, I might as well raise money and have people do the work for me. So I was told you should go into business. So that's what I choose. But fundamentally, why I choose that, I thought that was the most effective and the way to deliver impact. Is you are able to combine a little bit of that clinical, a little bit of that science, and take all the knowledge which is out there and bring it to help people. And which is still the same reason I went into medicine, is to help people, to help patients. And targeting aging is probably a more fundamentally better and more efficient way to help people than waiting for them to be sick.
Absolutely, I cannot agree more. Teresa, our research assistant at the Center for Health and Longevity, over to you. There are many questions.
Okay.
Thank you, Mr. Djordjevic, for your fascinating talk. So we have received numerous questions from the audience. Let's get started. Okay. First, in the early presentation, you refer that you mentioned 6 Yamanaka factors.
Yes.
As compared to the usual number 4. If so, what's the significance of the 2 extra ones?
Okay, so these 6 Yamanaka factors was the most, at least at that time, was one of the most universal and efficient combination to transform cells, I mean, from a normal cell into a stem cell. And in that context, it was as much of a cheat code, just because you're able to change the cell completely. But in the context of doing that, of trying to change the cell, we thought turning them into stem cell. You just want to rejuvenate them or turn back that clock, at least that methylation clock. So you don't need those 6 factors. Actually, it's a bit dangerous. These 6 factors, if you were to turn the cell into a stem cell, you could have teratomas, which is not very desirable. You don't want to get younger, but then have some of these small cancers. So the research has gone into trimming down and reducing progressively this number of factors to 4 factors, which are referred like OSKM, and then 3 factors OSK, which is what seems to be the general like consensus in terms of safety, in terms of what works best. In terms of cancer, we went a bit further, and we chopped bits and pieces of this transcription factor into even less, until it's like maybe 1.5, and doing it better. So that's maybe, but yeah, the starting point was 6.
Okay, thank you. Our next question, for how long must the reprogramming mRNA be expressed to rejuvenate cells? How is this time different from different tissues or organ types?
Well, it depends how much you want to rejuvenate and how much is safe to rejuvenate, and is different for every type of cell. There is some data you are trying to do. If you are trying to do a bit too much in the heart, well, in a way, when you are rejuvenating the cell, you are stopping the cell from doing its normal function. So if you stop the heart cell to make it rejuvenate, if you stop the heart from doing its function just to make it younger, well, it's nice, but if it cannot pump blood, then that's also not very practical. So I think it depends on where and what you're trying to do. And these are the kind of little details that we are going to learn into. I mean, the process is something which is beginning to be well understood, but then how to use it, that becomes a bit more of technical know-how and clinical know-how.
Yeah, thank you. Our next question is quite interesting. How would you respond to the critics who argue the following? The partial reprogramming won't make massive lifespan differences because it only allows small subset of genes to turn on or off. It is also difficult to perform experimentally. The current biological tools are limited to perform such precise multi-perturbation. It is inefficient and variable. There's a challenge in delivery and dosing.
Well, these are all very valid points, and it is, however, partial reprogramming, I think, is fundamentally is the right direction, and there is nothing else, I believe, in biology that can address as many of these hallmarks of aging at once. So if there is one way through which we could achieve something radical and substantial, I still believe it's through working on that. I mean, through partial reprogramming, especially in the close future. However, I mean, there will be a lot of problems, and I think there is a German saying where every problem has a solution, and every solution has a problem, and it's just a cycle. Things like the delivery, dosing, that's something that can be optimized, whether it's progress in using these viral vectors such as the AAV or the lentivirus, using these mRNA and liposomes, which in some way can seem to be a bit more efficient, and then we're even exploring completely different ways, also more novel ways to deliver a cargo into cell. I cannot say much, but then much cheaper and much more efficient. So these are the things that we are looking at, and it's something that's going to come in time, but you have to work. It's a bit like a software development. You just have to work, fix the bugs, and optimize and get better. And because every problem has a solution, and sure, it's a cycle, but yeah.
Yeah, thank you. Our next question is the driving mechanism known by which ER induces senescence in the cancer cells.
Okay. Oh, I think I missed. So it's not. To be honest, it's not very clear. Maybe. So there was another question. The one just before, like how does it know like what to change and what to remove? But it's. I think it comes to that's the part which is, to be honest, not very well understood. How does the cell know what is its, at least something as close to normal state or young state? And it is there, and I don't think we're exactly sure of why and where that information is stored, but it is there. And in the context of partial reprogramming, why it induces senescence, my personal hypothesis is like the cell is broken, is damaged. You have DNA damage and you have bits and pieces missing, and the cancer cell is going to do a terrible job. However, the information about what is its original function is still there in perhaps a different place. And when you apply that partial reprogramming, you are forcing the cancer cell to behave normally. And a cell that behaves normally, if it knows that it's broken, is going to suicide and die. I mean, however, in cancer, that mechanism through which like the cell would realize it's broken and dies is turned off. But then when we restore that normal function, even temporarily, maybe that's just what was needed for the cell to get senescent and die. So yeah.
Okay, thank you. Next, Since we can estimate the biological age from epigenetics, couldn't we try to program this to bring down the biological age and see if it is really does revert aging?
Yeah. So that's, well, I want to say that we can estimate some of the things, and biological age, it depends how you define age and how you define biological age. I don't think that's everything there is to aging. But I mean, yes, doing these, applying these aging clocks on the cell that had been reprogrammed does show a reduction in that biological age.
Do you keep an eye on work of various companies that are searching for other factors?
Yeah, so yes, that's something. Obviously, I have a team that has to look at what everyone else is doing. That's part of the job. And there is, I think, there are two groups. One, they're looking at, I think, broadly two groups. One is using transcription factor. The second is using these small molecules. You finding that small molecule, that little drug that you can pop like as a tablet, and that's going to do its job, is going to be a bit. It's going to take a long time. And I think I just lost my camera again.
Yes, we are again with the naked mole rat.
Yes.
Living long.
There we go. So, I mean, there are two camps in what they're trying to do. On our side, what our special work is, we're trying to trim down, in a way, make a special transcription factor that are going to do that job. That's one of that original technology. On the other side, there is this wild type transcription factor already doing a job good enough, at least for things like cancer. So there is no reason to wait for that perfect drug, for that perfect small molecule, for that new transcription factors, if this can already save people who are dying from disease. And perhaps it can be already applied safely on a more systemic level for people who don't have a specific condition but already age 80, 90, and the risk of dying are extremely high. So I'm happy to use something which is still a little bit dirty and not perfect, if it's something that can be done quickly. So yeah.
Okay, thank you. In the context of epigenetic reprogramming within the vasculature, have you observed an increased expression of genes typically associated with vascular developmental reprogramming? Specifically, do the programmed vessels exhibit characteristics closer to those of healthy mature vessels, or do they resemble early developmental vessels?
So they do resemble more like healthy mature vessels. There is this increase, I mean, in these factor things like VGF and other things linked to vessel growth. But yeah, is really restoring that, is not trying to change those vessels to something completely different. They just function in a more useful way. I mean, but that's something, there is a lot of data. I don't have it right in front of me, so I couldn't tell exactly which one, but yes.
Apart from tumors, what are most common adverse reactions to the gene factors?
Okay, I'm not sure I understand that question well. Okay, sorry, I see. So for this partial reprogramming, the initial way it was done was using 4 transcription factors, the OSKM, and this has shown to induce teratomas. Then the further experiments have where this has been trimmed to only 3 factors, the OSK, so OCT4, SOX2, and KLF4. Didn't show any of these teratomas forming, so these tumors starting to grow when you're trying to rejuvenate, say, animals. So except for that, if the question is there any other side effect? Well, I did mention earlier, if you are trying to reprogram perhaps the heart or the brain and you stop its normal function, even for a short time, that's not very desirable. So that's the things that will have to be watched out, is where we deliver that reprogramming, and probably do it segment by segment. You first restore the vasculature, for example, then you restore the liver, or you restore one by one in as safe a way as it is possible. But these adverse events is something we're only going to know for sure once we get into larger animals. We are preparing for primate studies in the next few months. So we will know a little bit more these adverse reactions. And I guess the time we're in human is the time we'll know for sure. That is for sure. But yeah.
Okay, we have got a last question from the audience. You mentioned the possibility that mole rats naturally express the factors that perform epigenetic reprogramming, and that this might be part of the reason NMRs have negligible senescence. Where can we read more about that particular research?
Okay.
Yeah.
Okay, so just a second, because I do have that one. So this was done, the work of a professor who specialized in ovarian aging from Cornell University. And let me just get that, the name of the person, because I always mix it up, so I don't want to say a mistake live. So here we go. Okay, from Miguel Angel Bueno Enriquez. The paper is called Postnatal Oogenesis Leads to Exceptionally Large Ovarian Reserve in Naked Mole Rats. It's a long, but you know, I can copy paste this here in the answer. There we go.
Thank you so much, Boris. Let us know what the reference is. Thank you so much for sharing not only the science with us, but also your thoughts as a CEO and the founder, and what keeps you actually awake at night. For the audience, there are two things I would like to announce. You might have heard already that we have a Founders Forum Unlock Healthy Longevity Conference happening at the 27th and the 28th of February here in Singapore. We are organizing at NUS this conference together with Founders Forum, but also together with Longevity Technologies, so with Phil Newman. And the conference is not only dedicated to academics and clinicians, but now we are mixing it up with entrepreneurs and especially also investors. So if you have a company and you're searching, we are going to matchmake. And we have a great lineup of speakers already. We are going to announce them from actually tomorrow onwards. And we have also different tracks that there's an investor track, there's an entrepreneur and an academic and clinician track. So hopefully we will see you there. We also have in the same week the intensive course on healthy longevity for healthcare professionals, where we on the 25th and the 26th of February, so 2 days beforehand, really try to inject the latest knowledge, evidence-based to healthcare professionals. So if you're a clinician, please possibly join. We all have QR codes on the slides, and if you want to have more information, go to our website, and that's longevityacademy.sg. As nearly every week, we have a webinar. On the 14th of November, Anna Milani will talk. She is the founder and CEO of Sparked Fitness. I can only describe the work of Anna Milani as talking about how to keep the brain fit in the gym. So not reading, no, going to the gym for the brain. We now close the webinar. Thank you for joining so much with a video, and that's also important for the brain, and that's about the mindset.
My name is Jimena Bogaví. I'm very proud to say I'm 76 and I come from Santiago de Chile. I had been 35 years working in a foundation, and then came my birthday number 70. I knew I had wrinkles, I know my hair was white, but what had changed was the way people were looking at me, and I didn't like it because they were all trying to protect me, imagining that I was going to fall or that I couldn't learn. And I said, well, that's funny. I mean, what's the matter with all of them? I'm the same. And I started talking to other friends, and they all said, hey, that's the same thing that happens to me. We decided to found Travesía 100, which means the journey to 100. And the purpose was changing the mindset about the way we were looking at age. Age as an opportunity and not as a problem. What we decided to do, first of all, was empower older people, Because some people retire and say, that's it. Those people tend to sit and get depressed. This is a moment to be yourself. It's a moment to do whatever you thought you were born to do. One of the things we've done with companies is help them understand who are their new, older clients. The other things we do is work with private companies to retain older people that are in their workforce so that they don't leave. Because if they leave, you will probably miss a lot of knowledge and experience they have. Some people attend our workshops and start studying a new career or join an NGO. What really energizes you? What makes you wake up in the morning with enthusiasm, say, I have something to do? This is a wonderful period of time. How can I give back what I have received? What can I contribute to society now? And that's a very powerful message to be alive.
I'm feeling like sunshine, like springtime, like something's in the water and I'm taking a deep dive. I'm feeling so weightless, like I'm gonna make it, and nothing in the universe can take this. I can see it clearly now, nothing gonna bring me down.